The next learning objective is going to be very similar to the last couple, ESS1-4.4, and this is I can justify the lengths of years of different planets using Kepler's third law of planetary motion. So the idea is that you could justify why Mars, for example, would have a longer year than Earth would, and Venus would have an even shorter year than Earth would. So can you compare and contrast the different planets and their orbital periods, how, their years, and justify why that would be the case using Kepler's third law? Let's take a start here. We got Kepler's third law, where we have the period squared is equal to 4 pi squared divided by the gravitational constant times the mass of the sun times the radius cubed. So the question we're going to ask is how many days will the orbit of Mars take? So for this one is what we call plug and chug. You just plug in the values and solve it. You need a few values. First off, you need the mass of the sun, which is 1.989 times 10 to the 30th kilograms. You need the radius. How far away is Mars from the sun? That's 228 billion meters. And then you need g, the gravitational constant, which is 6.67 times 10 to the negative 11th Newton times meter squared divided by kilogram squared. And what you do is you just plug it into the values here. After plugging in all the numbers, you get a monstrous value for period squared, but remember, of course, that was period squared. So we need to take the square root of both sides to get that the period is equal to still a rather large number. And we're going to write that in scientific notation. So we have the period is equal to 5.94, round to about 3 significant figures, times 10 to the 7th seconds. That's about 59 million seconds. Well, how many Earth years is 59 million seconds? When we do the unit conversion, divide by 60 again for minutes, and then hours, and divide by 24 for days, and divide by 365 for years, and we get that it's about 1.88 years. So how does the length of a year on Mars, for example, compare to that of Earth? And it's 88% more. It is longer by 0.88 of a year, so it takes 1.88 Earth years for Mars to go around the sun. Now that last example had a lot of really large numbers and a lot of unit conversion that we got to do, but it turns out there's an easier way to do Kepler's third law. But first, before we can work with this easier way, we need to define a special unit. This unit is called an AU. 1 AU is the distance from the sun to the Earth. It's just a unit that we made up to measure the distance from the sun to the Earth. And what we're also going to do is we're going to use period not in seconds, but in years. Previously I said you had to use it in seconds, but you'll see how this works out fairly nicely. So we're going to use our distance units are going to be astronomical units, which is the distance from the sun to the Earth, and our period is going to be 1 Earth year. And let's remind ourselves what Kepler's third law kind of looks like. Kepler's third law looks like the period squared is equal to some kind of constant multiple. This doesn't change, it's not a variable, times the distance between those two objects cubed. Let's just leave this as a variable, this constant, and let's plug in 1 year, square it, and 1 astronomical unit, and cube it. And then let's solve for what this constant must be. So you rearrange and find out that A must equal 1 year squared over 1 astronomical units cubed. What's important here is that notice that the numerical value of this A is just 1. This A, although it has some weird units going on, it only has the value of 1, which means we can write that the value, not including the units, we're not talking about units, just the value of period squared equals the value of r cubed if and only if the period is in years and r is measured in astronomical units. Now, remember, the units don't technically work here. We should still have some kind of constant here that's being multiplied that fixes the units for us, but we're just determining the magnitude of the period squared. We're not actually solving it and getting the correct units, just the number. If we just care about the number and not how the units work, then period squared equals the radius cubed if and only if we use this combination of astronomical units and years. This takes the calculation that we did previously and simplifies it greatly, so long as we know what the astronomical units are and we know what the Earth years are. Let's see an application of that. So here's the objective. We're going to use Kepler's third law to compare the length of a year on Venus to that of Jupiter. And we need some givens. So first off, the average distance from the sun to Venus, so also called the semi-major axis, and what we're going to use as r, because we're again assuming that everything is undergoing uniform circular motion, is approximately 0.72 astronomical units. That means it's about 72% of the way between the sun and the Earth. Because remember, the Earth has a value of 1 astronomical unit by definition. The average distance from the sun to Jupiter is approximately 5.20 astronomical units. So the sun, or the Jupiter, is about 5.2 times further away from the sun than the Earth is. And the question we're going to try to figure out is calculate the orbital period in Earth years for both Venus and Jupiter using Kepler's third law, and explain why Jupiter has a much longer year compared to that of Venus. We start with using the simplified Kepler's third law expression, where we're going to be measuring astronomical units in Earth years. So it simplifies neatly down to just the period squared of Venus, that's why hence the V subscript, is going to equal the astronomical units for Venus's orbit, cubed. So we find that the period, after we do the math of it, 0.611 years. So about 61% that of Earth's year. So when Venus has done a complete cycle around, the Earth has only gone about 61% of its cycle. Now, let's do the same thing, but for Jupiter. So Jupiter, we're going to be plugging in the 5.20 astronomical units, and then, of course, finding what the period of Jupiter would be. So according to our math, it would take Jupiter about 11.9 Earth years to complete its cycle. So that means you'd have to wait 12 years for Jupiter to go all the way around. If you're in my class, most likely you've only had a little over 1 complete cycle of Jupiter going around. In other words, if we lived on Jupiter, you would be only about 1 point something years old. So now I give it to you to practice. Here's a problem. Use Kepler's third law to determine the orbital period of a hypothetical planet in our solar system. So we're making up a planet. This planet does not exist. We're going to say that the hypothetical planet orbits the sun at a distance of 15 astronomical units. That is 15 times further away from the sun than the Earth is. Your task is going to be to calculate the orbital period in Earth years for this hypothetical planet using Kepler's third law, and compare it to the orbit of Uranus, which has an average distance of 19.18 astronomical units from the sun. So already we can tell that the orbit of this hypothetical planet should be quicker than that of Uranus, because Uranus is 19.18 astronomical units from the sun. The further away you are, the longer the period, the longer the year takes. Another thing to bring up is we could have done the opposite. We could have known how long something takes and placed its position somewhere between 2 planets. Like, for example, if we knew that it took longer than an Earth year, but a shorter amount of time to go around than a Mars year, we would know that distance-wise, it would have to be somewhere between Earth's distance and Mars' distance from the sun. So go ahead and complete that problem as part of your notes.